For our post-lab analysis, we need to figure out the molecular weight of the unknown. The problem tells us that the crushed unknown that we added has the empirical formula. This is the lowest common denominator of C3H2Cl. If you go to post-lab question number 6, they actually give you the actual molecular formula, which is C6H4Cl2. So this is the information that we're given. How close we can get to our actual true molecular formula based on the data that we got. So just as a review here, the pure cyclohexane melt freezing point, was 4.36 degrees. That's coming from weighing about 6.39 grams. And mixture 1, which contained 0.06 grams of the unknown, the freezing point went down. Remember, freezing point depression. And then when we added an additional 0.03 for a total of 0.09 grams, the freezing point went down from pure 4.36 degrees C to that of 2.06 degrees C. So let's figure out the molecular weight of this unknown, whose empirical formula is shown here. The equation that we're going to use is this here that we talked about in class, and that is the change in the freezing point temperature is equal to the freezing point depression constant. For cyclohexane, that was taken out of the textbook to be 20.5 degrees C divided by molality, or molal. The freezing point depression constant times molality, lowercase m. Now remember, molality, lowercase m, is moles of solute divided by kilograms of solvent. So let's figure out the molecular weight of the unknown, whose empirical formula is this, utilizing this equation. So first thing is we got our change in the freezing point. So that's going to be 4.36 degrees C pure minus, let's do it for mixture 1, 3.07 degrees C. So 4.36 degrees minus 3.07 degrees will give us the change in temperature. So the change in temperature here is 1.29 degrees C. That is T of F. Kf is a constant, and that's given to us here as 20.5 degrees C over m. Remember, molality, lowercase m, is moles of solute over kilogram of solvent. So we already have our first data table to look at here. The freezing point depression is 1.29 degrees C. So that's something we can put right here. So let's go now to the moles of the unknown added. The mass of the cyclohexane solvent that we weighed out was 6.39 grams. Okay, let's convert that to kilograms because, again, moles of solute over kilogram of solvent. So the conversion is this. There is 1,000 grams in 1 kilogram. The decimal place is 3 over, and we get 0.006639 kilograms of our solvent, which is cyclohexane. Now we need to figure out the moles of the solute, right? So remember what lower m stands for, right? So we have our change here, which is 1.92 degrees C. We have K of F, which is the constant we get. This lower m is moles of solute. That's what we want to solve for here, over the kilograms of solvent. We already have that here, which is what we weighed out, about 6.39 grams of it. So let's solve for mole of solute here. T of F change is 1.29 degrees C. K of F is 20.5 degrees C over m. The moles of solute is what we're trying to solve for, so I'll just leave that as is. Kilogram of solvent is this. All right, so let's take the 1.29 degrees C, leave it as is. We will divide the 20.5 degrees C, so we'll just do a little bit of a division here. We divide it, so moles of solute over kilogram of solvent. So this will be 20.5 degrees C, m divided by m, but the m gets flipped, so divided by m here, which is divided by moles of solute over kilogram of solvent. So that actually puts the moles of solute up in the numerator and the kilogram of solvent in the denominator, right? So 1.29 divided by 20.5. This lowercase m is moles of solute over kilogram of solvent. Because we put this in a denominator, already within a denominator, it gets flipped, equals to moles of solute divided by the kilograms of solvent. So now we have this value. Let's multiply both sides of the equation by 0.00639 kilograms. Okay, this is just units, it's not really a number. Okay, this should equal to our moles of solute. So immediately we see the degree C cancel, the kilograms cancel. So 1.29 times 0.00639 divided by 20.5 should give us the moles of the solute. And on my calculator, I'm getting an answer of 4.02 times 10 to the minus 4. And the units here are going to be moles. Okay, moles of this unknown. If we go back up, the unknown has this empirical formula. All right. So now we know immediately how to calculate the molecular weight. We do that because initially in mixture 1, we weighed out 0.06 grams. Okay, the units of molecular weight are grams per mole. So we have here, so this is for mixture 1, we weighed out 0.06 grams. Okay, this is how many moles that we got from our calculation. Doing this on our calculator, I'm getting an answer for our postulated molecular weight of the unknown to be 149. Let's keep some extra digits here, grams per mole. So that will be the answer to our data table into our postulated molecular weight. So let's fill this data table out together. So the moles of the unknown added is going to be 0.000402. 0.000402 divided by the kilograms of solvent, so that's going to be 0.00639. So let's do that on our calculator to get the molality. So the moles divided by the kilograms of solvent from our data, getting about 0.0630 lowercase m, okay, which is moles solute over kilogram solvent. Okay, mass in grams over the number of moles. So once again, just to reiterate, we weighed out 0.06 grams of the unknown, divided it by this many moles, getting about 149.253 grams per mole. The empirical mass of the unknown, they tell us, is C3H2Cl. So let's go ahead and calculate the mass from our periodic table. So here I'm going to use the periodic table values. Carbon is about 12.01, but we have 3 of them, so multiply by 3. Hydrogen is about 1.01, we multiply by 2. Cl in the periodic table is about 35.45. So adding those up, I'm getting about a molecular weight or molar mass of about 73.50 grams. Let's add that to our data table, 73.50 grams per mole. Okay, it's going to be the same for mixture 2. It stays the same. So the ratio of the molar mass to the empirical mass. So the molar mass we calculated here was 149.253, and the empirical mass is 73.50. So let's just take a quick ratio of the two. So we're going to do 149.253 divided by 73.50 to get sort of our factor. Okay, the factor that we multiply the empirical formula by. 149.253 grams per mole divided by 73.50 grams per mole. Okay, so the grams per mole cancel. And I'm going to use some extra digits here. I'm getting a factor of about 2.030. Okay, so 2.030. That is the factor that we will multiply the empirical formula by. So taking this factor, we'll just call it 2 for now. 2.0 times C3H2Cl. Or, well, I'll just multiply it all out here. So multiplying through like a train. And I'm just going to round it to whole numbers. Remember, these chemical formulas cannot have decimal places in them. So rounding this, I'm getting C6 on my calculator. Remember, I'm rounding here to the nearest whole number. H4 here and Cl2 here. And so that's the experimental molecular formula. And actually, that's pretty good because it matches what the post-lab question number 6 is asking us about. All right, let's figure out the accepted molar mass of C6H5Cl2. The accepted molar mass, we will have to use our periodic table values. So again, carbon 12.01, we multiply it by 6. Hydrogen 1.01, we multiply it by 4. Cl is 35.45, we have to multiply that by 2. And doing that on my calculator, I'm getting about 147.00 grams per mole. All right. But we got the molar mass of our unknown experimentally. Okay, this is from the textbook or periodic table. This is what we got from utilizing our math equations. We got 149.253 grams per mole. So let's figure out the percent error. So the percent error is known. So known is 147.00 minus what we got. What we got was 149.253. Known minus what we got divided by our known. Okay, I like to do, this is just me, I like to take an absolute value because I don't really like my errors to be negative, but negative error percentages, do exist. It just means that you are below the set or as opposed to above the set in your error. So doing this on my calculator and multiplying it by 100 to get the percent, this mixture 1 got a 1.53% error. So not bad. It's actually a very good one in terms of matching to what the lab tells us the true formula will be. Okay. So let's go ahead and do mixture 2 now. So mixture 2 has 0.09 grams total of the unknown, which we know is C3H2Cl. That's the empirical formula, the lowest common denominator. We're going to do the exact same thing as we did for mixture 1. We can now figure out the change in temperature. Let's go back to our data. All right, pure cyclohexane we calculated to be 4.36, and mixture 2, the freezing point dropped to 2.06. So let's take a subtraction here. And it's going to be about 2.3 degrees. I could do that math in my head here. So that's the change in temperature. So let's go ahead and fill out our data table here. This is going to be 2.30 degrees C. Now let's go ahead and figure out the moles of the unknown added. All right, so once again, delta TF is equal to Kf, which is 20.5 degrees C over molal. This molal is moles of solute over kilogram of solvent. So we know the kilogram of solvent, right? So the kilogram of solvent is going to be this converted to kilograms, so 0.00639 kilograms. And we know TF and we know KF. So I'm just going to put in the numbers here, 2.30 degrees C. And I'm going to divide it by Kf. We know Kf is 20.5 degrees C over m, moles of solute, kilogram of solvent, but that gets flipped. So now it becomes moles of solute on the numerator. It's just units now. Kilograms of solvent in the denominator. Okay, so I divided by K of F here. And this is going to equal to moles of solute per kilogram of solvent. Like we said before, the kilogram of solvent is nothing more than 0.00639 kilograms of solvent. Let's take this and multiply it out both sides to isolate and solve for moles of solute. So 2.30 degrees C. Let's just keep our units intact, times moles of solute, divided by 20.5 degrees C. Over m, but m is moles of solute, kilogram of solvent. When we do the switch, because it was in the fraction is in the denominator, so we flip the units, times, okay, multiplying this here, times 0.00639 kilograms of solvent. All right, so this is going to equal to our moles of solute. Let's cancel out some units. The degree C cancel. Kilograms of solvent cancel out with this kilograms of solvent. And we are left with moles of solute. So 2.3 times 0.00639 divided by 20.5. And our calculator, I'm getting, and so that's our moles of solute. The molecular weight has units of grams per mole. For mixture 2, we have a total of 0.09 grams. We weighed out 0.09 grams. The number of moles that we calculated is 0.000717 moles. So our units are grams per mole. Doing this on our calculator, 0.09 divided by 0.000717, I'm getting an answer of about 125.54 grams per mole. Okay, that's the appropriate units of molecular weight. Obviously, we know the moles. So the moles is going to be 0.000717. That's what we calculated solving for moles in this formula. So that's the moles in our second mixture. So moles divided by the kilograms of solvent. The kilograms of solvent was about 6 grams we weighed out. So we'll do that division and get our concentration in molality. So take this divided by 0.00639. So the concentration here is going to be 0.112 or so lowercase m. Remember, lowercase m is the same thing as moles of solute over kilogram of solvent. Calculated molar mass of the unknown is 125.54 grams per mole, divided by the empirical mass of the unknown we got from our periodic table is 73.50 grams per mole. The grams per mole and grams per mole cancel. And on my calculator doing that, figuring out our factor, the factor I'm getting is about 1.71. All right, so if you want to round it, it will be about 2. So let's go ahead and convert our factor, or multiply this factor through our empirical mass, just like a train. So about 1.71 times our empirical formula given to us of C3H2Cl. Right, it's going to be like a train, and I'm going to round this time. So 1.71 times 3, rounding that up is about C5. 1.71 times 2 for the H's, rounding that and being conservative in my rounding, that's going to be about 3. And 1.71 times the 1Cl, rounding that up, let's round it up to 2. Again, we never have decimals in our actual formula. So C5H3Cl2 is the experimental molecular formula, and it does not match the accepted one, unfortunately, but that's okay. That's our data, and we just have to do our best to defend it. All right, the accepted molar mass of this, the accepted is what we get from our periodic table, so it's going to be the same, 147.00 grams per mole. And finally, the percent error for our second mixture. So we take known, which is 147.00, that is something we get from the textbook or the periodic table, minus what we got 125.540 divided by known. I like to take the absolute value. Some scientists don't do that. It's perfectly legitimate if you do it either or. And doing that, we're getting about 14.69, 14.70% error. The second mixture, when we added the additional 0.03, we got a kind of a big error. Also, our empirical formula really didn't match the formula that they told us in post-lab question number 6. But this is the walkthrough on how you do your data. Your data and your numbers are obviously going to be a little bit different, but this is how you're going to do a similar type of calculation for your post-lab analysis. Figure out this question here in terms of errors. What happens if there's some sort of contamination or evaporation that occurs? The first question here is some cyclohexane evaporates while the freezing point of pure cyclohexane was being measured. So again, let's look at our formula here. Change in our freezing point is going to be that constant times lowercase m molality, which is moles of solute over kilogram of solvent. So let's say theoretically that some of the cyclohexane evaporates. So some of the cyclohexane evaporates. This denominator actually goes down. The whole fraction actually goes up. All right, so that whole fraction goes up. Now when you get your molecular weight, the molecular weight is in grams per moles of solute. Okay, grams per moles of solute. When your moles of solute has gone up, okay, in the denominator, what happens is that your overall molecular weight as a fraction goes down. So this happens whether the cyclohexane evaporates before or whether the cyclohexane evaporates after you add your unknown. So just sort of skipping ahead to part B, the answer here is that because it's grams per mole, how much you added per moles of solute, remember we calculated this by itself. We isolated it and calculated it in our calculations above here. So the answer to both A and B is calculated molar mass of the solute will go down. So we would expect it to go down or decrease. Okay, whether cyclohexane evaporated before or whether it evaporated after the addition of our unknown. Okay, so that would be the answer for part A and B. Again, it's having to do with the factors and the ratios, particularly what happens to the fractions. Once again, the kilogram of solvent evaporates, making this whole thing much larger, but grams over moles, the moles have gone up, the denominator has gone up, the overall fraction of the molecular weight, grams over moles, will go down. Foreign solute was present in the cyclohexane. This is kind of tricky. A lot of people who stumble upon this. The correct answer is that it doesn't matter. As you see, that error perpetuates. So let's say there is some sort of contaminant, and we calculate our freezing point. Then we add our unknown. That error gets transmitted and propagated across all other measurements. So we should not see much of an effect. So the answer here is no effect. Once again, there was a contaminant in the cyclohexane. We calculate the freezing point of the pure cyclohexane. We add our unknown. Nothing has changed. The contaminant is still there. It just propagates along with the rest of the experiment. So it does not have any effect on your calculated molecular weight, molar mass. And then also the same thing with part D. The error propagates. So if you're off by a temperature of 1.5 degrees C when you calculate cyclohexane freezing point, that's 1.5 degree error, whether it's low or high, just gets shifted to all the other measurements, and it sort of results in no effect. Okay, this will not affect the calculated molecular weight, the calculated molar mass. Okay, we would expect these errors to sort of propagate throughout the course of the experiment.